If we're to look at the very outer scale of the Smith chart, we'll notice that it is labeled wavelengths towards the generator, and it's got an arrow that points clockwise, right? And what that's telling us is that we've got this scale here that's measured in units of wavelengths, and it tells us that to move from a load towards the generator a distance of L wavelengths, we need to rotate clockwise around the operating circle. So why would we ever want to do that? Well, that's what you're doing when you're figuring out what the input impedance of a load connected with a certain length of transmission line is. You've got your load and you normalize it, right? Z is equal to ZL over Z0. So we calculate our load impedance. And if we were to plot that kind of on our Smith chart, we will get that operating circle, right, where that is the normalized impedance Z right there, let's say. We draw our line from that, from the center of the Smith chart to that operating point, and if we rotate this arc clockwise according to the gradations on the Smith chart loads towards the generator scale, what that does is it moves us in lengths of lambda along a transmission line, right? So to determine the input impedance of a transmission line of a certain length measured in lambda connected to a load ZL using the Smith chart, what you do is you first calculate the normalized load impedance. You then draw the operating circle for the point. You then draw the line from the center of the Smith chart through the normalized impedance point out through the perimeter of the Smith chart, all the way through the outer scale. What you then do is you rotate clockwise by the value of the electrical length of the transmission line. What you'll have to keep into account is that one full rotation around the Smith chart is equal to 0.5 lambda. So every time I rotate 360 degrees, I've repeated 0.5 lambda. For line lengths that are greater than 0.5 lambda, what you're going to have to do is subtract off multiples of 1/2 lambda until a value between 0 and 1/2 lambda is reached, and you'll use that new value for rotation. And finally, when you complete your rotation, what you'll do is you'll mark that point, and then you'll draw a line from the center of the Smith chart to that point. The intersection of that new line and the operating circle gives you this normalized input impedance. So as most things, I think that's best understood using an example. So what we want to do is we want to determine the input impedance of a circuit that's got a transmission line, characteristic impedance of 50 ohms. It's 0.15 lambda long, and it's got a load of 40 minus J20. So step one is normalize. Normalized load impedance is going to be 40 minus J20 divided by the characteristic impedance of the transmission line. So that's 0.8 minus J.4. The next thing we need to do, step 2, is to plot the point on the Smith chart. Plot Z on your Smith chart. So I've done that down here. This is different than other examples we've done. This is minus J4, so that puts us on the bottom port, or minus J.4 puts us on the bottom half of the Smith chart. So I've plotted that. Step 3, draw operating circle. So here's the operating circle. We've drawn that. Step 4 is what we want to do is we want to find where a line drawn from the center of the Smith chart through the normalized impedance point, we need to figure out where that intersects with the wavelengths towards the generator scale. So step 4 is you draw this line right here and you figure out what that value is right there on this outer scale, the wavelength towards the generator scale. And that is, the answer to that is going to be wavelengths towards the generator is equal to 0.395 lambda. And I'm just reading that value off from right there. Step 5 is we need to rotate by the length of the transmission line. So step 5 is that we're going to do 0.395 lambda plus 0.15 lambda, and that is equal to 0.545 lambda. So that's the total length of the transmission line that we would have to rotate. We would go from, we rotate 2.545 lambda, but remember that we can't rotate further than a half lambda, so we have to subtract off 0.5 lambda, which leaves us 0.045 lambda. So what we then do is we find on the wavelength towards the generator scale, we find 0.045 lambda right there. So this whole rotation right here is the 0.15 lambda of rotation. We then draw this line right here, extending from the center of the Smith chart to that 0.045 lambda on the wavelengths to the generator scale, and we mark Zn, which is the intersecting point of that line and the operating circle that we drew in step 3. So step 6 would be to draw line to 0.045 lambda. Step 7 would be mark Zn. In this case, we see that it's 0.64 plus J 0.175. Now, that's a normalized impedance. To get back to an unnormalized impedance, capital Zn, we need to multiply by Z0. So that's, in this case, 50 times 0.64 plus J 0.175. And that gives us an input impedance for the circuit of 32 plus J 8.75 ohms.